Welcome back. This is the second segment of section 7.3. Likely we'll have 3 segments in total because, as I've said previously, these problems take quite a bit of time to solve and to do them well. So you have to kind of mitigate that when you're looking at a testing situation, that sort of thing. But hopefully the first one will take a little bit longer because I want to point out some pitfalls and places where you can make mistakes, and then I'll probably come back for a third segment where I solve another sort of the last version. So we'll solve a side angle side in this segment, and we'll probably come back for a side, which is a lot more straightforward. It might not be that long of a segment. So without further ado, let's get started here. The first thing we want to do is we want to set up a situation where we have a side angle side. Now, it turns out because we don't have this so-called ambiguous case when it comes to law of cosines, there is no situation in which we pick, no matter what values you have for side angle side, you will always be able to produce a triangle. Now, it does happen to be the case that you can construct a situation with side where you don't end up with a triangle, but it's because of something called the triangle inequality. If the two sides don't add up to at least the third side, then there's no way for them to meet in the middle, so to speak. But that's kind of an unusual case, and I won't bore anybody with that. So let's kind of set the stage here. This is section 7.3, and I believe I'm on page 3 now. So let's create a side angle side situation. Let's take angle B equal to, or hold on. I want to create one where we might create the ambiguous case if we do this incorrectly. So let me do angle B equal to 24 degrees and side A equal to 43, let's say, feet. So sine, and I'm just trying to make this up on the fly. So times 43. So it needs to be a little bit more than 17, but less than 43. Let's make side B side C. Let's make this. Let's make it very, very large. How about I don't know, 165 feet. I think we'll end up with a situation there. Let me just do a quick check. 43 squared plus 100 plus. Well, I guess we'll find out. So in this situation, we've got a fairly shallow angle and a really, really long side. So it's about 4 times the length. So this one might give us the ambiguous case, or it might not. So here, this is 24 degrees. So this is B. Side A, let's call this side A. This is side C. So this is side B. Angle A, angle C. So I've kind of taken what I've been given in terms of the dimensions, and I will try to, I've kind of drawn the triangle that I think is the solution, but we'll do it in a more formal way. So now I have the situation where I have one side, another side, and an angle. And as a result, I will want to use the version 1 of the law of cosines to find the third side first step. So first step will be find B, little b, which is equal to, if you recall, all these numbers will be positive. So we can sorry, when we, in version 1, both the left and the right-hand side are positive, and the result should be positive. So we end up actually taking the square root of both sides of those equations to find the lengths, which normally when you take the square root of both sides, you have to insert a plus or minus, but b is a length, so it's never going to be minus. So this will be the square root of a squared plus b squared, sorry, not b squared, a squared plus c squared minus 2ac cosine of b, all under this radical. And to put in the values, this will be the square root of 43 squared plus 165 squared minus 2 times 43 times 165 times the cosine of 24 degrees. Now, this can get a little bit complicated using my calculator because of order of operations. So again, what I'm going to do is I'm going to start over here on this. I'll take the cosine of 24, then multiply, 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 change the sign, and then add these squared terms. So first off, 24, cosine of 24 is about 1 times 165 times 43 times 2. And then I'm going to change the sign so it's negative. Then add to that 165 squared, and then add to that 43 squared. And notice I now have a number 16,000 something or other. So now I'll take the square root of this, and I end up with 126.92 blah blah blah. So 126.928 whatever. And remember, this is side B. So I'm going to store this number. So I would say store 1. So in memory 1 is actually side B. Now at this point, and I'm gonna say now, it may not make any difference because I think B is too small to make any difference. But I just want to point out that at this point, I now have angle B, side A, side C. And it is real tempting to want to go in here and say, all right, well, I can, now that I have angle B and side B, I can use side C and to find angle C by using the law of cosines, or sorry, the law of sines. But notice that is the ambiguous case. And so if you look at this, it looks like that's probably just based on how I drew this, that is probably an obtuse angle. And what you'll end up with, and maybe if I just state this, here is a fact about triangles. The measure of the angle is in descending or ascending order. So if A is the largest angle, then the side opposite A must have the largest length. If B is the middle angle, then the distance opposite B should be the middle distance, and then the angle C opposite C should be the smallest, or vice versa, or whatever. So that it's preserved, the order, the ascending or descending order of the size of the angles is not equivalent to, but it is preserved in the lengths of the sides. Now, there's not a direct relationship. It's not like you say, well, take 12 degrees and multiply by whatever. No, that's not how it works. But they are, you don't end up with a situation where somehow, B is the smallest angle, but the side A is actually the shortest side. So just looking at this diagram, which if I've done it right, you would expect A to be the smallest length, which is actually bears out, right? Because B and C are actually longer. So we probably don't end up with a problem here, although we certainly could. So let's let's see what would happen if we, and you know, maybe I'm creating more work than we actually need here. But I just want you to be careful because there are certainly situations where you try to use the law of sines here and you don't adequately check to make sure that you've got the right kind of situation. Um, and you could end up with a calculation that produces something that is just completely bogus. Um, so anyways, and that is primarily because you've created the ambiguous case of the law of sines. So once you go, like I said, once you go down this road of using the law of cosines, you need to stick it out. So the next thing in the progression would be to find angle A. So recall that angle A is equal to the inverse cosine of the other two sides, so b squared plus c squared minus a squared, all over 2 times b times c. And I'm going to start by working in the denominator. Now remember, this number I have stored is side b. It's the one that I'll need for all of them. So I've got b times c times 2. So I'll just go ahead and do that. So b times 165 times 2. So that's the denominator. I'll take the reciprocal. And then I will multiply this by b squared, which is, recall 1 squared, plus c squared, which is 165 squared, and then subtract 43 squared, close the parentheses. There's my number that's going to come out of that's the argument of inverse cosine. And it is in the range of cosine, which we expected. So I will now take the inverse cosine, and I end up with 7.29 degrees. Sorry, 7.9200866, etc. degrees. Now at this point, I could use that and just use the fact that triangles add up to 180 degrees. And so I could just, you know, add it up that way. But rather than taking that shortcut, let me just do that sort of quickly as an aside. So if I wanted to find angle C, C is going to be equal to 180 minus 24 minus this 7.92 yada, yada, yada. So I would come up with 148.0799, etc. Notice that that's an obtuse angle. And this is a quick and dirty calculation to come up with this. But because I have the ability to check, I probably should check. But in the meantime, I'm going to come back to this here in just a second, because notice if I had instead of calculating A first, but had maybe calculated C and tried to use the law of sines, note that the relationship would be, let's see, I have B, I did calculate B, so I have sine of B over B equal to sine of C over C. Now, when I try to solve this, I'll end up with what, sine of C equal to C over B times sine of B, which will give me an answer. I mean, I have a quantity there. Let's see what comes out. So the next step would be to take the inverse sine. And this is the problem, is I don't know whether this angle is obtuse or acute, but it's very easy to make this mistake and just say, well, okay, let me just take the inverse sine and C over B, sine of B. Since I'm just doing this as scratch work, so I've got C, which is, angle B is 24 degrees, so 24 times sine of 24 times C, which is 165, divided by B, which was, I actually have that. I don't know that I had it. We'll type it in. So 126.92828 and some change. And then we take the inverse sine. Now notice that's 31.92 degrees, which just happens to be the supplement of what we actually calculated. And so here's sort of the quandary you get into. If you decide to switch to a different method here in the middle, you'll actually not be able to determine which of these angles is the correct. Is it supposed to be this one, or is it supposed to be its supplement? Because there's not enough information to determine it. And that's why I'm saying never change to a different method. Once you start with the law of cosines, stick it out and use the law of cosines, because the law of cosines doesn't have an ambiguous case. Anyway, so I don't want to belabor that too much, but let's go ahead and finish the problem here. So we had page 4. So we already had all three sides. We had angle A and angle B, and then we calculated angle C using the sum of interior angles equal to 180. But let's verify and what we got was 148. But let's verify that we get the same result by using the second version of law of cosines. So C is equal to the inverse cosine of A squared plus B squared minus C squared over 2AB. And again, I'm going to come back to B. So recall one. So B was 126. I'm going to multiply that by A, which was 43, and multiply that by 2. Take the reciprocal. Then multiply by parentheses A squared, which was 43, plus C squared, plus B squared, which was this weird number, squared. Then subtract from that C squared, which is 165 squared. Take the division. And notice that's a negative number. And that's okay, because this is going to give us an angle in quadrant 2. And that's exactly what we would expect to get out of this. I know we haven't done too much with inverse cosine, but that is the net result. So let's take the inverse cosine of this number, and we end up with, again, 148.079913, etc. degrees. Okay, so to summarize then, what values did we come up with? So we've got A is, now, if we look back at this, A is 7.92. The question is, where do I cut this off at? Well, look where the calculations come from for A. We have a number B that we use the full Monty here, but it's derived from calculation. Here we have something that is accurate to the feet, right? C actually has more significant digits. It has 3, but A only has 2. And then you're dividing by something that has sort of, I guess, 2-ish, 3-ish. But the limiting factor is right here. Something with 2 significant digits. And so when you take the inverse cosine of something that's only really got 2 significant digits in all the inputs, then this will have 2 significant digits. So A is equal to 7.9 degrees, which is kind of a little bizarre. And I'll show you why. Because when you then find, well, B was given. And remember, here's C calculated using the law of cosines. We also got basically the same number when we used the interior angles equal to 180. But notice this only has 2 significant digits, right? Same argument can be used for this. It should only have 2 significant digits. So C, round this thing off to 2 digits, is 150 degrees. Yikes. Um, Now, A was given as 43 feet, and B was calculated as 126.9 yada yada yada, but it's derived from a series of measurements that that only had two significant digits at best. So this thing should only have two significant digits, which means it's 130. And then finally C, which was given, is 165. So here we have this really bizarre mismatch between these different angles. And notice if you add up the angles, they're going to be way above 180 degrees. They're going to be like 181.3 or 181.9. But that is because of this of the parameters of the significant digits rules. And I will tell you that in my experience, this would be the wrong thing to do because you would end up, having just all kinds of a messed up situation. So typically, when I have people do these problems, I will ask them to, I will tell them what digit, what place to put it. But to be completely fair, this is what you're supposed to do with these significant digits. But this is where it starts to get a little weird. And if you tried to compare, if you like plugged in these values and put them back into the equations, you wouldn't get the angles either. There's all kinds of mismatch here. But regardless, this is, according to the rules, this is the correct solution. Okay, so I'm going to finish here segment 2. I know I kind of got a little long-winded there, but I will come back in segment 3. I'll probably even start on the same page and set up a side, side, side. It's very quick because we only use the same sort of formula over and over and over again. We just do it 3 different times, and there's no ambiguity. There's no way to actually make a mistake, so to speak, unless you just really are crazy. So I will see you back in the third and final segment.